I'm trying this a second time because last time it kind of didn't work out well. First thing we're going to do is basically do integers. So it's n factorial, which is equal to n parentheses n minus 1, so on. Anyways, this is definition. Basically, you're gonna realize that this is gonna be our definition giving because with this we can actually do the proof. This is algebra, but we can't say anything unless we have a proof over here. Because think about it. Why is 0 factorial not equal to 0? Well, it's because if we use this given as our definition, we get the fact that over here, we find when we do the algebra, it becomes 1. Therefore, it isn't really working out. Basically, what's happening is n factorial is equal to n minus 1 factorial n. If you divide that by n over here, basically this goes away and this equals n. And if you plug in 1 over here, this equals 1 because 1 factorial of 1 is 1. Basically, this is equal to 0. And that's how you get 0 factorial. Anyways, from that, I wanted to talk about that because I forgot last time. And then we're gonna move on over here. We're just gonna go on over here because there's no point. The next one we're gonna do is summation here. So this is summation, which is 1 plus 2 plus 3 and so on to n. With that said, the reverse is 2, which is n minus plus n minus 1. The same thing, it's just inverse. If we add those together, we realize it's n plus 1, n plus 1, n plus 1. And there's n of them because of this. With that said, now we get this formula over here, which is going to be divided by 2. And this q, don't forget, is equal to the summation of I. Therefore, it's true. Over here is next, which is going to be I squared. I squared is a little interesting. You're going to take the a cubed to get a minus 3. We already did the proof for this one, so I'm not really into getting more of this. Instead, we're going to plug this I into this concoction. Basically, you get this afterwards. Um, no, sorry. This is the first thing we're going to do because this equals this, basically. And you figure out why, because this goes to 1, allowing it to simplify to this over here. And then it keeps on going to this format over here. It's just algebra. And we're going to use first use of telescope. Telescope means basically that you can cancel this out, cancel this out, cancel this out, cancel this out, and so on until you get to here, which is n3 is left over, which is the left-hand side or right-hand side, or whichever you're going to say, whichever you want to say. So over here next, you find that you do the other side of the whole thing, which is basically over here, this side. No, this side, sorry, this side over here. And you plug into here with the n's cube over here, and then you do individually to get this. We already understand what this is from earlier, which is n parentheses m plus 1. After that, it's just algebra. After you do the algebra, you get this formula in the end. Now, the polynomial theorem is interesting. The first thing you need is a base, because what we're going to do is basically say plus 1, n plus 1. So n equals 0, and also it's probably some I don't know who actually created it, but I'm pretty sure it's like it's either Indian or Middle Eastern. Um, anyways, first thing I'm gonna do is 0, 0 over here, and then that equals 1, which is the same as if we were to do it this way. Now we're gonna do n equal 1 because 0 is a special case always, so I'm always iffy to use 0 as our base number. So over here we get 1 and we do all the algebra to get n plus 2. By the way, this bracket means this over here. So anyways, after that, we get n plus 1. And what I'm trying to do here is basically if I push this to plus 1, then every single n plus 1, n must equal to n plus 1. And that allows us to say this is valid if the previous one, so it's basically saying if n at 1 is true, then I can say n at 2 is true because you're just adding 1 to n. And then you can say so on forever and ever for all the n's. So basically, that's what I'm trying to do. Over here, I plug in our previous definition into here to see if I can actually get that. And multiply by So it's just a little trickery because you're making this into x plus y, and you're just disputing it to get this form. And you're multiplying the original function, this thing with x, original function of this to y, and getting this form as a result. And with that resultant form, we'll do a little bit of dummy variable manipulation to get this out of here because we want this side, and this side to be the same looking as this, or try to. Anyways, because it is dummy variable, we can just because it's just indexes. Basically, you can just do j equal k, and after that, you realize that this one over here has a plus one, and over here there's a zero over here. So zero can be removed like this, and then the n plus 1 can be equal to this. You can just plug in n to k and see that this is actually 2 and this is actually 2. And because of summation, you're just adding it up. Now we do this proof, and it's just algebra manipulation. You can double check that if you want. And if you add all those up, if you get all those up to this form, we realize we are indeed correct, and basically everything is correct. Now, Bernoulli's number, there's also Bernoulli's function, but that's from a PDE. So we're not really talking about it. And actually, I'm hesitant to use this one, but because it used Taylor series over here. But so I'm just going to skip it for now, but I made it. But basically, I made it for this Fromberg's formula. And in reality, all you need to know is that this is found from it because this takes calculus to derive. So just note that this is possible from it. Why I'm doing this is because if you want to look at it in more detail. And also over here, this thing, I know how to derive all this, man. By the way, this over here, basically, you can get it from doing this stuff, but it's just a pain in the ass, so there's no point to it. So I'm just giving you it basically. Um, I guess you could just write down a cheat sheet or something. Anyway, we go to vector. I start with this one because it's visually like this is x direction, this is y direction. Then I do a little bit more of that, and then go to polar form 2, basically showing off that one point you can do polar form like this. Maybe I should also explain Euler's equation, but I didn't. And maybe I should have. I also explained adding vectors, so adding these two vectors. I didn't label B. I should have labeled B. I'll do that later. Why did I not do that? I don't know. And then addition and subtraction, and a little bit of getting all the forces in the x direction and the y direction, and doing all that stuff, and log cosine, log sine, and a little bit of determinants over here. Basically, I should have wrote down clear, but this over here is basically a vector, and this over here is a vector, I think, if I remember correctly. You can see that vector over here as these two. Yes, and then this one over here, and then that forms this area over here. Maybe I should explain more here, but it kind of works out, I guess. I don't know. I did a little bit of problems and then with 3D determinants over here. Thank you, this guy that made it. This Pango domain also so lovely. So you can get the area of of a pipetoid over here, pipa whatever it's called. Anyways, what is this? Dot product. Dot product is basically a way to get projections and particularity or something like that. Yeah. And then there's some properties of it. I haven't finished it, so that's pretty much all I'm going to say over here. And I'm going to stop recording now.